Hello, I'm SA, your AI essayist. Please note that all content, audio and video in this presentation are AI generated. As AI can sometimes produce inaccuracies, I encourage you to verify any factual information presented. With that in mind, let's begin.
The year 1925 witnessed a seismic shift in our understanding of the physical world, a revolution largely attributable to Werner Heisenberg's seminal contributions to quantum mechanics. This period marked an inflection point, transforming physics from a primarily classical realm to one governed by probabilistic rules and quantized properties. This essay undertakes a scholarly exploration of the intellectual landscape surrounding Heisenberg's work, dissecting its genesis, core tenets, immediate impact, subsequent evolution, and lasting legacy. The seeds of Heisenberg's breakthrough were sown in the fertile ground of theoretical physics, particularly in the challenging arena of atomic structure. The earlier Rutherford model, depicting the atom as a miniature solar system, faced significant conceptual hurdles. Classical electrodynamics, under Maxwell's framework, predicted that accelerating electrons should emit electromagnetic radiation, rapidly losing energy and spiraling into the nucleus. This contradicted experimental observations, which revealed the stability of atoms and the discrete spectral lines of emitted light. A Bohr model, while introducing the crucial concept of quantized energy levels, remained a hybrid, combining classical mechanics with ad hoc quantum postulates. This model, although successful in predicting the hydrogen spectrum, possessed inherent limitations, unable to consistently explain spectra of more complex atoms or to fully resolve its foundational inconsistencies. Heisenberg, deeply dissatisfied with the reliance on unobservable electron orbits, sought a more fundamental description of atomic behavior. He began his work by focusing on observable quantities, such as the frequencies and intensities of spectral lines, which provided an empirical window into the atom's inner workings. This methodological choice, a decisive break from classical intuition, would prove to be the cornerstone of his approach. In the summer of 1925, Heisenberg, grappling with hay fever, retreated to the island of Helgoland. There, away from the academic distractions, they formulated the core concepts of what would become known as matrix mechanics. Heisenberg's key insight was the replacement of commuting variables, central to classical mechanics, with non-commuting ones. He realized that quantities like position and momentum, which could be determined simultaneously in classical physics, exhibited a fundamental uncertainty at the quantum level. The mathematical formalism he developed relied heavily on matrices, a concept unfamiliar to many physicists at the time. Heisenberg's formulation of quantum mechanics was not immediately accessible, generating initial bewilderment among his colleagues. This was not due to a lack of intellect, rather, the mathematical language itself was novel in the context of theoretical physics. In essence, his mathematics described the interaction of atoms through these non-commutative algebraic structures. This departure from classical determinism had profound implications. It implied that the state of a quantum system could only be described in terms of probabilities, where observable quantities can only be determined. Heisenberg's work immediately provided a way to calculate the spectral lines of hydrogen, and it also illuminated the way for further developments in the. Upon his return from Helgoland, Heisenberg collaborated with Max Born and Pascual Jordan. Born, a leading expert in applied mathematics, recognized the underlying mathematical structure, a matrix algebra, and Jordan provided the necessary mathematical formalism. Their joint publication further clarified and solidified the mathematical underpinnings of the theory. In short order, this collaboration yielded a systematic theory of quantum mechanics. The impact of Heisenberg's work was immediate and transformative. It provided a consistent and mathematically rigorous framework for understanding atomic phenomena. It explained the discrete nature of atomic spectra, predicted with accuracy the intensities of spectral lines, and paved the way for the calculation of transition probabilities. Furthermore, the theory's non-commutable algebraic structures offered a fundamental explanation for the stability of atoms, resolving the paradoxes that plagued classical physics. Soon after Heisenberg's initial work, Erwin Schrödinger developed wave mechanics, describing quantum phenomena using a wave equation. These two apparently disparate formalisms, matrix mechanics and wave mechanics, initially appeared distinct. Schrödinger himself viewed Heisenberg's matrix mechanics with distaste, yet the equivalence of the theories was demonstrated by Schrödinger himself and subsequently by others, thereby revealing the underlying unity of quantum mechanics. Their work clarified the mathematical language. The two approaches, despite different starting points, described the same physical realities, the wave function in Schrödinger's equations, and the matrices in Heisenberg's. Each represented a complete description of the quantum state. This conceptual unification enriched the framework. The legacy of Heisenberg's work extends far beyond the immediate success in explaining atomic spectra. His formulation of quantum mechanics served as a foundational pillar for all subsequent developments in the field. The core tenets of quantum mechanics, the quantization of energy, the wave-particle duality, the uncertainty principle, the probabilistic nature of quantum events are all rooted in his matrix mechanics. His work has profoundly influenced the development of various subfields of physics, including quantum electrodynamics, which describes the interaction of light and matter, and quantum field theory, the theoretical foundation for the standard model of particle physics, as well as a variety of applications and technologies. Heisenberg's work, however, was not without its critics. Initial resistance came from those accustomed to a more visual and intuitive approach to physics. The abstractness of matrix mechanics, with its reliance on non-commuting variables and intricate mathematical formalism, initially presented a challenge to comprehension. This challenge was exacerbated by the fact that the mathematics was largely unfamiliar. Physicists struggled for some time to come to terms with the counter-intuitive concept of uncertainty, which clashed with the deterministic worldview of classical physics. Despite these initial challenges, the theoretical framework was consistently validated by experimental results, which led to its eventual widespread acceptance within the physics community. The influence of Heisenberg's work extends beyond the immediate confines of quantum physics. His focus on observables and the abandonment of classical determinism influenced the broader landscape of scientific thought. This fostered a re-evaluation of the nature of reality and the limits of human knowledge. This also spurred developments in epistemology and philosophy of science. His emphasis on the role of the observer, an essential aspect of quantum measurement, changed how we view scientific experiments themselves. This also encouraged a deeper examination of the interpretation of scientific theories. The influence of Heisenberg's work on other scientists and their subsequent contributions stands as a testament to its transformative power. Schrödinger's development of wave mechanics, though initially presented as an alternative, ultimately became another facet of the quantum theory. Paul Dirac, in his seminal work, synthesized the theories. He built upon the matrix mechanics and wave mechanics, combining them with special relativity. Dirac developed a relativistic quantum mechanics, which accurately explained the behavior of electrons at high speeds and predicted the existence of antimatter. Wolfgang Pauli, working closely with Heisenberg, utilized the framework to develop the Pauli exclusion principle, a cornerstone in understanding the structure of atoms and chemical properties. In conclusion, Werner Heisenberg's 1925 contributions to quantum mechanics represent one of the most significant intellectual achievements in the history of science. His methodological shift to focus on observable quantities, his embrace of non-commuting operators, and his formulation of matrix mechanics provided the first complete and consistent framework for understanding the quantum realm. Beyond its immediate successes in explaining atomic spectra and stability, the work catalyzed the development of modern physics, impacting fields such as quantum electrodynamics, quantum field theory, and materials science, to name a few. Any scholarly evaluation of Heisenberg's work must consider its influence on a vast range of fields. The enduring legacy of his work continues to shape our understanding of the universe at its most fundamental level.
We really appreciate you tuning in to this AI-powered presentation. Our goal is to push the boundaries of AI in content creation, and your input is invaluable. If there's a particular subject you'd like to see us tackle next, or if you have suggestions on how we could fine-tune our AI's creative prompts, please don't hesitate to leave your ideas in the comments section. We're excited to bring you more unique content very soon.